Buenos días. Vamos a comenzar con la segunda sesión. Será mayoritariamente en inglés, pero con algunas cositas en español. Habrá primero dos charlas de 20 minutos de José Antonio Lozano y Scott Waters, y luego comenzaremos con la sesión de Early Career de jóvenes investigadores e investigadoras, en la cual habrá 5 charlas de 15 minutitos cada uno, y posteriormente pues la sesión de preguntas. Good morning. We are now going to begin session 2. It will be primarily in English, and we will have 2 talks by José Antonio Lozano and Scott Waters of 20 minutes each, and then we will begin the Early Career Researchers section with 5 talks of 15 minutes each, and then we will have the general Q&A and discussion. Our first speaker is José Antonio Lozano Rodríguez. He's a senior scientist here at the Canary Islands Oceanographic Center from the Spanish Institute of Oceanography since 2021. He holds a degree in geology and a PhD focused on rock formation processes in the seafloor, both from the University of Granada. He collaborates in studying volcanism from the Neogene and recent time in different zones such as Antarctica, the Iberian Peninsula, Canary Islands, Japan, Iceland, New Zealand, etc., as well as applied geology. He has published over 30 high-impact research papers, another 30 book chapters. He was part of more than 25 projects, national and international. He's also an invited expert at the PEVOLCA Scientific Committee. And currently he's co-directing a doctoral thesis at Sevilla University and a Marie Curie postdoc focused on landslides in the Canary Islands. And he's also co-leading a research project about carbon fixation in olivine-rich beaches in Tenerife. This talk will be in Spanish. The rest of the talks will be in English, but you're welcome to ask any questions in English in the Q&A session. Esta sesión va a ser en español, el resto será en inglés. Pero en la sesión de preguntas pues se pueden hacer preguntas tanto en español como en inglés indistintamente.
Muchas gracias. En primer lugar, quiero dar gracias a la organización, que he vivido de primera mano lo mucho que han luchado. Son vecinos míos, Eugenio, Sharon, Alba, Juan Pablo, Eduard. La charla que voy a dar yo es sobre las pilus, sobre todo las megapilus que se produjeron en el volcán, en el delta submarino del volcán de Tajogaite, en La Palma, sobre la erupción de 2021-2022, que trabajamos muchísimo en la erupción y seguimos trabajando en ello. A título de curiosidad, pues pongo una presentación que se hizo en el Museo del Cosmos, en el cual pues pudieron ir más de 45.000 personas. Bueno, pues el índice lo voy a pasar porque lo van a ver y tengo poco tiempo, lo que voy a explicar aquí sobre las pilulabas. En primer lugar, la metodología. Obviamente tenemos que utilizar los barcos oceanográficos del Instituto Español de Oceanografía, del CSIC, Ángeles Alvariño y Ramón Mangalet, para hacer sobre todo ecosonda multihaz, para determinar cómo era el fondo marino antes de que llegaran las lavas al fondo marino y después cuando llegaron las lavas. También se utilizó pues, el PISCES, el submarino de Scott, que está aquí presente, que ahora después hablará. Ahí se puede ver una imagen, luego hablará él, de cómo es el interior del submarino, donde caben 3 personas, él que va aquí pilotándolo y 2 científicos a cada lado, o una imagen de cómo es el submarino por fuera frente a una de las megapilus de este delta del volcán de La Palma. Esas imágenes y esos vídeos y las muestras son también recogidas gracias al ROV Liropus 2000. Aquí pongo una imagen de cómo se cogen esas muestras de una pillow a 120 metros de profundidad. Y para hacer una introducción geográfica y geológica, pues obviamente sabemos que la erupción se generó en la parte de Cumbre Vieja de La Palma, con toda esta extensión que pongo aquí en colores en cuanto a áreas, ¿no? Generándose dos deltas lábicos, uno al norte y otro al sur, siendo el del sur, que es este que vemos aquí, mucho más grande que el del norte, teniendo mucha menos erosión que el que está teniendo el norte. Si no me equivoco, son unos 30 hectáreas de lava delta submarino y unas 53 de lava delta subaéreo. La imagen esta la pongo porque luego entenderán cómo repercute sobre la formación de las pílulas megapilus, que es el grosor de estas lavas. Esta parte de aquí es conocida por todos ustedes, es el gran talud, el gran tajo de unos 80 o 90 metros que tuvo que superar, en este caso de modo descendente, las lavas para poder formar los deltas. Y en color amarillo se puede ver los grosores, es decir, se tiene que suavizar, como luego veremos, esa pendiente para favorecer la formación de las pilus y sobre todo las megapilus. Es interesante y creo que es muy importante conocer cuáles son los tipos de vulcanismo. Rápidamente diré que el volcán tuvo una diferenciación magmática en la base de la corteza oceánica a esta profundidad de unos 12 kilómetros, donde apareció un tipo de lava algo más félsica de tipo tefrita, y posteriormente a mitad de octubre ya se incorporó una lava más profunda, que es una basanita y que discurre por encima. ¿Por qué digo esto? Porque esa última es de mayor temperatura, es más fluida y menos viscosa. Eso repercute a la hora de formar estas pilus que veremos aquí. En amarillo se puede ver cómo llegan primero estas. Creo recordar que la lava tarda unos 9 o 10 días en llegar al mar, así que llegan parte de esas lavas, pero posteriormente todo el delta es formado por estas otras lavas más profundas y más fluidas. Aquí se puede ver de dónde aparecen esas primeras lavas, como digo, algo más viscosas, y luego con posterioridad aparecen estas otras que salen mucho más profundas, de aproximadamente unos 40-38 kilómetros de profundidad. En un diagrama de los que solemos utilizar los petrólogos TAS, pues se puede ver cómo evolucionan desde una tefrita, no sé si se ve bien, a una basanita, ¿vale? Imágenes muy conocidas ya por todos de cómo llegan estas lavas al mar formando el delta. Aquí pongo una imagen, parte de ese delta sur, que es el que más vamos a estudiar por sus dimensiones, aprovecha un delta ya preexistente del año 1949. Esto ya es una imagen de cuando el volcán dejó de funcionar, como es el aspecto general que se puede ver en foto aérea, ¿no? Con el barco pues pudimos hacer la topografía antes y después de lo que son los deltas lábicos submarinos. Esta de aquí sería la lava, el delta lábico norte, y esta de aquí sería el delta lábico sur, donde ya se puede ir apreciando todos los lóbulos de estas coladas de lava que entran dentro del mar prácticamente como si no hubiera agua, ¿no? En esta imagen se puede apreciar muy bien con una línea blanca cuál es todo el área que ocupan estas lavas. Incluso se puede ver cómo las más meridionales tienen una dirección hacia el noroeste, y sencillamente eso ocurre porque van ocupando antiguos cañones submarinos del talud proximal. En esta otra figura se puede apreciar cómo conecta todos los flujos del delta subaéreo con estos otros lóbulos de los flujos submarinos. E incluso hay un momento en el que se puede ver cómo cambia esta parte de aquí más profunda con una viscosidad mucho menor y más fluida con respecto a estos otros. Ahora lo veremos. Con ayuda del ROP hicimos varios transectos que se ven aquí, el 19, el 13, el 18, para poder observar y hacer una descripción geológica, un transecto de qué materiales hay aquí, pudiendo ver pues, flujos de grano, hialoclastitas, megapilus con colores morados, pilus, brechas angulares, brechas mucho más planares y sobre todo, fijaros en azul que corresponde a esta parte de aquí, todas las brechas correspondientes a las lavas AA. Es decir, todas estas que señalábamos anteriormente, estos 6 lóbulos que hay aquí corresponden a las lavas de tipo AA. Y bajo ellas vamos a ver cómo fluye todas estas lavas que son de un comportamiento, como decía, menos viscoso y más fluido. En este cuadro es muy significativo porque se puede ver a qué profundidades aparecen las megapilus. Esto es solo y exclusivamente para megapilus. Aparecen a todas las profundidades y las dimensiones. Algunas de ellas llegan a los 4,5 metros de diámetro. Es una barbaridad. Y de longitud entre 10 y 15 metros algunas de ellas. La petrología muy por encima, bueno, también es necesaria porque ejerce un poder muy importante en la generación de estas pilus y megapilus. Sobre todo, en un primer vistazo podemos ver que apenas hay vesículas, es decir, están desgasificadas. Las lavas llegan prácticamente ya sin gas, han desgasificado en la erupción volcánica al principio, porque si tienen gas, las explosiones son muy grandes y no se puede producir pilu ni megapilu. Hablando de la geomorfología, creo que esta imagen es muy significativa, porque ya de un solo vistazo se puede ver cada uno de los lóbulos con sus respectivos LED, puestos aquí en azul, con sus deformaciones, que son, al igual que ocurre como los glaciares, pues labios que quedan en el movimiento de flujo pendiente abajo, o este otro, o este otro. Y todos los frentes de estas lavas, que curiosamente quedan parados sin movimiento aproximadamente entre los 50 metros de profundidad y los 60 metros, quedándole todavía más de 40 metros de plataforma para llegar al talud. Pueden ver en este color, color marrón, todo el área que comentaba antes que ocupan estas lavas deltas submarinas, y en blanco la trayectoria de uno de los ROVs que hicimos, que es el 13, donde se describen muy bien todos estos materiales que estábamos diciendo. Haciendo un corte justo aquí donde pongo el punto A', que es el borde de estas lavas de tipo AA, se ve algo muy curioso, y es que obviamente, como decía antes, ocupan esos cañones submarinos y suelen tener unas potencias enormes, aquí hasta 17 metros. La más meridional, incluso se observan muy bien los leves de los que hablaba antes, y las lavas van a fluir por debajo fundamentalmente de esta y de esta otra de aquí. Se puede, no sé si lo ven, se puede apreciar aquí. La pequeña sería esta, discurre para acá, y esta otra de aquí. En un corte más distal, B', que es este, pues también se puede ver que esa lava, que aquí ya es más fluida, también ocupa un cañón submarino y está desplazada gravitacionalmente debido a que es un comportamiento pues fluido. Y creo que el más significativo es este corte, que sería el corte desde aquí, C', este de aquí, donde podemos ver todas las lavas de tipo AA que han quedado totalmente congeladas aproximadamente, como decía, a los 50 o 60 metros de profundidad. A partir de ahí aparecen una brecha composicional y pilu, y luego, cuando aumenta la pendiente, van apareciendo pilus y megapilus. Lo curioso es que estas profundidades corresponden o coinciden con el cambio de temperatura en profundidad. Puede estar relacionado ese momento de frenado de las lavas tipo AA con esto, pues no lo sabemos, estamos estudiando eso, porque también podría estar relacionado con la presión hidrostática que se produce con respecto a la profundidad. Algo que creo que es de vital importancia es el papel que juega este acantilado, este tajo en la formación de las pilus. Antes de llegar vemos un tajo que, como digo, tiene aproximadamente unos 80, incluso hay sitios con 90 metros de altura, y cuando llegan las lavas van, permitidme la expresión, goteando, como se pueden ver en estas imágenes de aquí. Y van generando la progradación de estos lóbulos del delta submarino, y luego otros que van progradando encima de ellos. Solo y cuando la pendiente se suaviza porque van cayendo más coladas, que serían los ejemplos estos, de aquí o aquí, fijaros ya la pendiente que tiene aproximadamente 30-35 grados, se ve muy bien. Solo ahí es cuando ya se pone en contacto toda la lava que viene del volcán con la que está generando las pilus, porque necesita las pilus continuidad. Para ver un poco la geomorfología de ellas por encima, pues bueno, aquí tenemos una imagen espectacular desde mi punto de vista de estas megapilus con más de 1,5 metros y que se amorda perfectamente al sustrato. Luego las que vienen por encima se amordan entre sí, entre ellas. Y algunos ejemplos de esas dimensiones, 2,30, 3,30, 4,50 metros. Esta imagen es muy significativa también para entender cuál es la génesis, porque en los sitios donde hay mucha pendiente, la pilu es más pequeña. En los sitios donde hay algo menos de pendiente, aunque sea sutil, las pilus suelen ser algo más grandes. Os voy a poner un vídeo, por favor, Alba, puedes darle al vídeo, porque una imagen vale más que 1000 palabras. Esta sería 95 metros de profundidad y con pilus de 0,90 y un megapilus entre 1,35 y un poquito más. Se pueden ver todas acomodadas unas a otras que proceden de otra más grande. Es decir, que en profundidad a veces van perdiendo lo que es dimensión. Salió de nuevo, ¿no? Vale, pues aquí hay otro vídeo, no sé si le doy, aquí sale. Estos son a 161 metros de profundidad, son muchos metros. Y tienen como 1,20 aproximadamente, se puede ver muy bien todas las señales. Mirad cómo ahora va a girar un codo perfecto de pilu justo aquí. Y ahora va a haber una brecha de colapso, muy bien, se va a ver ahora de colapso porque se vacía por dentro, como un tubo lava. Se vacía y se ve muy bien la brecha de colapso. Ahí sigue otra vez la pilu, ¿vale? Para ver un poco así, pues la geomorfología, la estructura de ellas, pues bueno, hay de todo, desde brechas tabulares, grandes pilus, yo creo que esta imagen también la puso Eugenio, que son de 2 metros, 2,5 metros de ancho, pueden llegar incluso hasta los 15 metros. Algunas muy interesantes, como el frente de la pilus se apoya sobre el talud, sobre la pared del talud, o todas las estructuras estas muy características de corrugación, que ahora veremos, o fracturas transversales, y sobre todo algo que les caracteriza mucho es estas fracturas en caparazón de tortuga. Esta imagen no he conseguido que se vea mejor, me tenéis que creer, esto tiene 4,5 metros, son enormes, está a unos 104, 105 metros de profundidad. Detalle de cómo son estas estructuras de corrugación, aquí se ven algunas, a 123 metros de profundidad, o las hialoclastitas, generadas justo en el frente de la pilu, que con el contraste pues va cayendo. Ahí tenéis un pulpo de escala. Y os pongo pues a menor profundidad, a 6 metros, pues cómo son estas otras lavas mucho más viscosas, menos fluidas, que son las de tipo AA, ¿no? Son exactamente las brechas bajo el agua iguales que las que se pueden ver por fuera del mal país. Las estructuras dibujadas yo creo que se entienden algo mejor. Aunque ustedes saben cómo funciona esto, pero bueno, una lava de tipo AA pues funciona como una cinta transportadora y la brecha que se va enfriando en contacto con el aire aquí y aquí abajo también en contacto con el suelo, la de arriba, parte de ella suele caer abajo en su avance. Cuando esto para y solidifica, pues aparecen todas las deyecciones columnales que todos conocemos aquí en la isla, ¿no? Esas son las imágenes de cómo es la brecha por fuera, pero es que en el mar es igual. Y las pilus y las megapilus, pues muchas de ellas están bifurcadas. Y aparecen, como decía antes, pues colapsos de brecha en el interior de algunas de ellas, ¿no? Con su estructura en caparazón de tortuga. Y bueno, puedo leer algunas consideraciones, pues la compleja arquitectura de las facies correspondientes a las partes meridionales del delta sur sugiere la propagación de la lava en 6 lóbulos discretos emplazados secuencialmente. Bajo el lóbulo más meridional de lavas AA aparece una red de tubos de lava interconectados que se propagan ramificándose, generando las primeras pilus y megapilus, presumiblemente desde una sola fuente. Los 3 lóbulos más importantes de lavas tipo AA se detienen antes de llegar al talud a unos 50 y 60 metros de profundidad. Está relacionado con la termohalina y o la presión hidrostática. Y luego alguna consideración en relación con la génesis de las megapilus, pues se genera en flujo de distales con tasas de suministro de magma más bajos, eso es importante. La tasa de suministro de magma más altas produce facies de lámina gruesa. El bajo contenido en volátiles facilita la formación de megapilus, evitando en parte la fragmentación explosiva. La baja viscosidad de las lavas facilita que fluya más fácilmente. Ejemplo, pues las lavas de tipo Pajoé con composición basanítica, que son muy pobres en sílice, alto contenido en hierro y magnesio. La mayor extrusión de la lava facilita la formación de megapilus con flujos continuos y sostenidos, superando el enfriamiento rápido inicial y ayudando a su crecimiento en expansión masiva. La superación del acantilado, eso es importante, facilitó la formación de megapilus. La baja velocidad de enfriamiento, en este delta submarino, la temperatura del agua no fue un factor importante, encontrándose megapilus a diferentes profundidades. la altura de la presión hidrostática, aguas profundas, pues ha de influir algo. Y por último, el entorno submarino, como la poca pendiente y la irregularidad de la misma, hace que el flujo discurra lentamente. Pues muchas gracias.
Gracias, José Antonio, bastante interesante, además te has ajustado perfectamente al tiempo. Thank you so much. Now we are going to welcome Scott Waters for the next talk. Scott Waters is the founder and senior pilot of the PISCES VI submarine, which is a deep diving human-occupied research submarine that can go up to 2,000 meters depth. Previously, he trained on the American deep submersible vehicle Alvin submarine at the Woods Hole Oceanographic Institution. And Scott is also an airplane pilot, mechanical technician, and also works as a consultant for human spaceflight with government and private agencies. So, welcome, Scott.
Okay, so, yep, I'm Scott Waters. I'm originally from the United States, but I live here in Tenerife now for 4 years. And a little bit about the PISCES VI submarine. So I was interested in science and human-occupied exploration, both underwater and in space. And I was doing a career that was completely different. And I had the opportunity to change my career. I was always interested in submarines. And I started thinking, why is there not more deep diving submarines in the world? The only ones that exist are the United States deep diving submarine, the Alvin, the French deep diving submarine Natil, the Japanese Shinkai, and the Chinese Zheolong and Fendoza. And so all of these are attached to very large institutions that have the funding to run a program like this. And one of the things that it was not being done is it being done privately. I was really inspired by watching SpaceX be able to do things much faster and much more efficiently than government institutions. So I started looking at how could this be done. My original idea was to buy a used deep diving submarine from an institution, and most of these existed in Russia. I spent 4 years trying to negotiate with Russia to buy one of their submarines, and it didn't work. And I got very lucky because PISCES VI, which was previously a scientific submarine doing work with National Geographic and Dr. Eugenie Clark with Deepwater Sharks, the submarine came up for sale. So we ended up coming up with a plan of how to get the submarine back into service. It was originally built in 1976 by the International Hydrodynamics Corporation in Canada. And it became a much bigger undertaking than I expected. So I hired a team of engineers and specialists from all over the world, and the submarine community is very, very small, and I had a lot of help. So the Woods Hole Oceanographic Institution, I owe a lot to them for taking me under their wing, training me, and any question I wanted to know. And then also at the time, the Hawaii Undersea Research Lab, which was operating PISCES 4 and 5, and was specifically studying volcanoes and hydrothermal vents. So this is the specifications of the submarine. It's currently certified to 2,180 meters and was designed for 2,500. The reason that we don't go to 2,500 at this point is because the testing tank that we had in Southwest Research Institute in Texas could not go that far. So that's why the weird number. We also come with a large suite of scientific equipment that we own on site, but then also the submarine network is very, very small. We have the opportunity to borrow from other groups, and specifically when it comes to volcanic studies. So a while ago, I actually, way back when I came to Tenerife for the very first time in 2016, I met this guy here, Eugenio, and he was really, really interested because he had previously been down on the submarine Yago and El Hierro. And he said, we have to have this. We have to find a way to use this with our institution. So one of the things we need to do is demonstrate the capability of a deep diving submarine and why it's important. For those of you that have used a deep diving submarine, such as Thibault and France with the submarine Alvin, they understand it. They understand why it's an important asset to the scientific community. And we have the ability to do a lot of sampling very fast, very precisely. But one of the things that is so unique, and it's very hard to explain until you've experienced it, is the perception that you have by going deep yourself and seeing with your own eyes rather than through a camera. And it's a huge thing that we took every single one of the directors, and we took a few other people down with us that got to experience this so they could really understand why this is important. So Eugenio had this idea when La Palma happened of, hey, let's take the submarine out there, but not only do we want to use the submarine, we also want to do rosette studies. We want to dive with a ROV. We want to explain this capability that Spain has and show it all at one time. And so not only did we dive the submarine and do this research, but we also took down the ROV and dived in tandem. It's a very uncommon thing to do because it's so difficult and it requires very skilled pilots like Bernardo over here. And we were able to dive together, and this is how we got some of the most amazing images of Pisces looking at this volcano with scientists on board. So one of the really amazing things that Pisces can do, unlike any other DSV in the world, is a huge cost is getting the submarine on site. For example, on the Alvin submarine, it's $65,000 a day to move it. And when they have to relocate, that's just money that's accumulating. When we redesigned the submarine, we said it had to do two things that no other submarine can do. One is we have to be able to transport anywhere in the world very, very inexpensively. And then the other is we need to be able to operate in marine protected areas. And that requires a few special things. One is that we only use water ballast. So we don't drop anything to the bottom of the ocean. We leave no trace. But then also we have ultra quiet capability. So for example, operating in Los Gigantes in the marine protected area with the whales, we don't disturb that, and we can prove that capability as well. So this is us mobilizing, getting ready to go to La Palma, and we just put the submarine on a truck, and the other container is our mobile shop. We have the ability to be autonomous at sea for months at a time. We can do onboard repairs and maintenance, so this is the capability that we've produced. And then once we arrived in La Palma, one of the problems we had at the time is that we did not have a ship big enough to handle the submarine. The submarine weighs a little under 10 tons, and so we need a special crane to do that. And now we do have the capability with the Adon de Boyne, the brand new ship. It does have the capability to handle Pisces. But at the time we were using the Ramon Maugalef, and we were operating from shore. And we just took a crane, put it right in the water, and we towed to the location. We're able to do 2 dives a day, every single day, with the exception of one day where we had extremely bad weather, which was very rare. But that's the type of capability that we want, is to be able to dive over and over and without any kind of delay. So this is a picture that I have from from inside the submarine looking at the ROV. And again, this is a very difficult thing to do, is to coordinate these operations, but we're able to do it really well. And with 2 companies that had never worked together before. And so not only was it to gather images, but really to display the capability and also have additional capabilities that were previously unknown. We took a lot of cool people down on this dive. Some of you recognize as your faces in here. And then we also produced a documentary that will be airing sometime soon on Amazon Prime with Jesus Calleja, and we took the astronaut Pedro Duque down with us. But it was really cool for a lot of these scientists that have been studying these systems but have never seen it before in their actual life with their own eyes, to be able to take them down there. And for me, I guess the thing that I really, really love is being a sponge. Yes, I'm piloting the submarine, but I love learning from the scientists, and it just fascinates me more. So this is a video. I don't know if you have to. Yeah, there we go.
Like a channel.
Yeah.
Like that.
So this is just a whole entire group of lava just going straight down in a finger. Wow.
So we actually had cameras going. I just filmed this on my phone because I thought it was really cool. But it was really fascinating to go down here and see these lava tubes, and you can get perspective of what is happening with the lava tubes when they hit a flat spot, and some of them even start going up and over ridges, and you can see where they split. For example, here it was a system of a whole bunch of tubes all coming down together. And it was really nice because we could go down and look at these, and the scientists at the time could say, actually, can you go a little more over here? Or could we get closer to that? Or could, in an example, we can also, with a submarine, you can say, I want to take this sample. And with the PISCES, we have the ability to take a lot of samples. And a lot of different kinds: water samples, gas samples, rock samples. And this mission, like I said, was more of a demonstration, but it really gives us these kinds of capabilities. A mission that we just did in December and November, just here in Rat Azul, is we were doing a new species identification mission in partnership with Oxford University and the Nippon Foundation. And in just 10 dives, we discovered 17 new species. And it's really cool to see the science happen right before your eyes. So this is just a small amount of the team. I don't think we got everybody in the picture, but it was really, really fun to watch so many different groups, the ship, the ROV, the submarine, and a whole bunch of different scientists all work together in unison. And I really owe it to Eugenio of coordinating this, because it's very difficult to do that. And he made it look like just completely flawless. And it was really cool to see, because there's challenges. We had weather, we had multiple platforms deployed at one time that all had to be managed. And it really does take a lot of experience to be able to do this. But we really hope to be able to do a lot more, not just other kinds of research, but specifically volcanic research. And this is maybe one of my most favorite photos that I've ever seen of the submarine. And we've seen it a few of the slides here. But one of the missions that we are putting together for next year is actually planned to be one of the biggest human exploration missions of hydrothermal vent systems in history. And so we're working with the governments of Iceland, the Faroe Islands, Norway, Portugal, and Azores. And we're looking at all sorts of different hydrothermal systems, from the north of Iceland of white smokers down to the Azores for example, the Lucky Strike black hydrothermal vent system, and then over to the seamount by Portugal, which is the serpentine vents, which are really interesting as well. So we're in the process of putting this mission together for next year, but it's looking like it'll actually be a 3-month mission at sea, and with cooperation from multiple different governments that all think this is really cool. But one of the things that we're really excited about is that we have, as maybe you heard, my background's also in space. And so actually part of the groups of scientists we have on here are astrobiologists that are looking for origin of life and to apply this science to Mars and the icy moons of Jupiter and Saturn. So it's actually, not only are we studying volcanic systems here on Earth, but this research extends on to a lot of different kinds of science. And it's really neat to be able to have the first, with PISCES VI, the first volcanic research that we did right here in the Canary Islands. And like I said, I owe a lot of this to the Hawaii Undersea Research Lab group as well, that pioneered a lot of the hydrothermal vent exploration in Hawaii, and the Alvin group that really, they found the black smokers and some of the things that they brought to science. And even with the speech that we just saw, they're doing this all the time. And so it's amazing that we were able to land here in the Canary Islands thanks to the deep water, the collaboration with the Spanish Oceanographic Institution and the universities. And really, we hope to continue to do this kind of science because it's truly amazing.
Thank you, Scott. That was really interesting. Looking forward to what you're going to do in the future. So now we're going to begin with the early career researchers section. I'm just going to say a few words in Spanish. Vamos a comenzar ahora con la sección de jóvenes investigadores e investigadoras. Quería hacer un inciso muy rápido para resaltar que Vulcana, como proyecto y como grupo de investigación, desde sus inicios ha hecho una apuesta muy fuerte por apoyar a jóvenes investigadores e investigadoras. tiene un componente muy grande, muy importante de formación en todos los niveles, desde grado, máster, predoctoral, postdoctoral, y no solo formación, sino también con contratación joven, además contratación digna, que no siempre es fácil de encontrar en estas etapas. Así que, bueno, esto obviamente es un esfuerzo de financiación y de dedicarle tiempo, así que, bueno, quería agradecer sobre todo a Eugenio y también, por supuesto, que siempre ha estado respaldado por el Centro Oceanográfico de Canarias, el Instituto Español de Oceanografía y el CSIC. Así que muchas gracias. Y bueno, ahora para darles una pequeña muestra de que efectivamente merece la pena apostar por los jóvenes y las jóvenes, pues queremos enseñarles un poquito lo que hemos estado haciendo. Así que primero voy a dar paso a mi compañero Juan Pablo. So the first talk will be by Juan Pablo Martín Díaz. He's a PhD student here at the Spanish Institute of Oceanography. And also with the University of La Laguna. He graduated in environmental science and holds a master's degree in assessment and environmental monitoring of marine ecosystems. And he's interested in the effect of physical chemical perturbations on the ocean caused by submarine volcanoes especially. And currently he's studying his focus on the submarine hydrothermalism of Tagoro as an environmental stressor, although I think now he's going to deviate to a different system, which is very interesting. So, Juan Pablo.
Thank you, Alba, for your introduction. And also, I join you to your very nice work for this director that we have here, and also for our group, Vulcana. This group, Vulcana, was also collaborating with another oceanographic center to describe all the hydrothermal system that is in the Columbretes Island next to Castellón. Here we have the archipelago that is around 55 kilometers off the Castellón coast in the Mediterranean Sea. This place is quite important for conservation. It's a marine protected area. We have a unique species here, endangered species. There is a cetacean migration zone, and also for seabirds. So that's very fragile ecosystem and very, very important to be protected. But also we have here in this square our study area where it was visited 2 times in 2 different cruises, where we found this mound, the Calent mound. Well, that is like the hydrothermal system is about 35-50 meters depth. It's mainly located in these spikes here. And here we describe the different physical and chemical parameters in the water column, mainly temperature, salinity, pressure, dissolved oxygen, pH, ORP, fluorescence, and all these properties were measured at 24 Earth. That means that we have 24 values per second. So we have a lot of data here. We used 2 different strategies to survey this area. The first one, we used our sensor that were mounted in the oceanographic rosette. And our main objective was just to identify this field and try to know the limits and also how the activity was distributed along this mound. So that's why we mainly move our sensors very close to the seafloor, just 3-4 meters above the hydrothermal system. And And then the next year, so we have here the mound and all the area that we sampled. And then next year we came back here with another objective, just to know how this impact or this affection of the hydrothermal fluids could have in the water column. So in this second year, we used another strategy, that's the TOYO strategy, that the sensors were moved up and down while the boat was moving forward. So that's why we have all these transects going up and down along the mound. But also, we sample water and also the gas fluxes from the bottles that were coupled in the rosette and also by divers to know the nutrient concentrations and DNA samples to know the bacteria diversity and the CO2 fluxes. So from the hydrographic survey, we know that the main affected area was located about 35 and 50 meters depth by using this Brun-Weissala frequency that is similar to the buoyancy frequency that use the density of the seawater to see the instability of the water column. So when we see all these spikes here, it means that some instability is happening there, and the water parcel is moving upward or downward just to find the stability. And you can see that all these, or mainly all the spikes, are located in this region. And then using independent sensors and another sensor like the pH and the ROP sensors, they say the same, that all these anomalies are located in this region in both years. The first year, for example, we had an anomaly, a maximum anomaly of 0.5 units of pH. And in the second year, we even reached 1 point of anomaly of pH. That's a lot in the sea ocean. So then once we have all these vertical profiles, we wanted to know how they were distributed in this area. So here we have the horizontal distribution in this mound where we see the transects and the region where all the anomalies were located. And just to give you an idea, the region with an anomalies of pH of more than 0.05 units were more than 70,000 square meters. That it was like 40% of the mound. And the same for the 0.1 anomaly and a negative anomaly of 0.2, that it was almost the 2% of the mound. But what is important here is just to see that an anomaly of 0.1 unit is the negative pH that is projected to be decreased by 2050. And we are already registering here. So that's important just to create some monitoring study for the ocean acidification studies and so on. But also, we also register a negative anomaly of 0.5 unit that is also projected to be happening in 2000 and 2100. But then that's what's happening in very close to the seafloor. But we also wanted to know what was going on the water column. And that's why you see here this transit here from A to B. That was the transit that we sampled the next year. And it's this majestic dome that we have here that is almost covering the whole mound. You see the movement of the sensors that is covering the whole mound, the whole hydrothermal system, and it reaches up to 10 meters above the seafloor. That's a lot, and also covered almost 800 meters long. Yeah, more or less. So here we have also a maximum anomaly of 1.12 unit that is located almost in the same place as the previous year. But here we, yeah, we were able to catch it, but probably the previous year was already there, but we couldn't find it. And for example, this plume of a negative anomaly of 0.1 unit covers almost the whole surface, and it's about 1,500 square meter. Then with the nutrients concentrations, we measure them in 3 different regions and the reference areas where they're not affected by these hydrothermal fluids. Then above the hydrothermal system, there is the CTD samples, and then the samples collected by the divers directly from the hydrothermal vents. And we see there is a huge difference of concentrations, and the samples from the vents are significantly enriched compared to the reference, and also compared to the water samples from the a couple of meters above the system. And also we even detected enrichment up to 200 times the reference concentration. That's a lot. And then we sample the bubbles from this area. Here we measure the fluxes from 14 different vents during 5 hours of video, just to try to see if they were emitting bubbles in a continuous mode, or it was in a random periods or regular periods. And to know that, we applied the fast Fourier transform analysis that it divide all the periods along all the frequencies, and we see the different intensities of each period. And if they are up the horizontal lines, it means that this is that deep vents had significantly periods of emission. That means that it emits regular pulses of gases at some point. And here we have the wavelet analysis that we see if these pulses are emitted during the survey that we made. And you can see here that all these intensities are like very continuous. So we can say that all vents were emitted in a regular way, and also along the time that we were sample all these samples. But then we also wanted to know how many liters of CO2, or the amount of CO2 that these vents were releasing. And for that, we divided all the vents from this area in 3 different groups with continuous fluxes, intermediate, and low fluxes. And we saw that the continuous fluxes are about 200 35 kilograms of CO2 released in a year. And then if you see, and this is only for one event, but we have in this group 5. So you can multiply this amount for 5, and you will have a very huge amount. But then we did a very conservative estimation just to see how much is this amount in a year, and we estimated that in this area of this picture, that it was around 10 square meter, it can release 100 tons of CO2 per year. That is similar to more than 20 cars in a year. That's only for one bend. So you can multiply for 14 and you will have a very huge amount. And that was all. Thank you.
Thank you so much. And now it's the turn for Alba González-Vega. You have been growing so fast. I remember you when you were here doing your master thesis, and now you became a professional. She's working and she's doing a really great job. So I'm really pleased to meet you and to be a part of our team. So congratulations. So Alba holds a PhD in oceanography and in global chain. Her research focuses on the effect of the submarine volcanism on the physical and biochemical properties of the marine environment, scoping different events such as submarine eruption, hydrothermal venting, and lava-ocean interaction, particularly in the two most recent eruptions in the Canary Islands. Her interests also expand to the scientific assessment during marine emergency, and she has worked in different crises such as oil and plastic spills or the perturbation in the Mar Menor ecosystem. She has also participated in international scientific committees such as European Marine Board or the Commission on Submarine Volcanism of the IEO-CSIC, International Association of Volcanology and Chemistry of the Earth Interior, and since 2022, she is a contracted researcher at IEO, so she's in our team right now. So this stage is yours.
Thank you. So hello again. Okay, we are coming back to the Canary Islands, and now we are going to see another volcano that we have here, very close to us. It's Enmedio volcano, and it's quite deep and not very well known so far. So we're going to present a work that is currently in the process of being published, which evidences that there are some hydrothermal activity in the Enmedio deep submarine volcano. So first, a little bit of introduction. Enmedio literally means in the middle, for those who don't know Spanish. So it's in between the two most populated islands, Tenerife and Gran Canaria. And just some general information, the summit is at over 1,600 meters below sea level, and the deepest parts are more than 2,000 meters below sea level. It has an elevation, irregular elevation between 500 to 700 meters, more or less, a diameter of around 3.5 kilometers. And apart from this main big cone, there are more than 10 smaller cones in the area, which we will see more in detail later. So there is not a lot published about this volcano. A few papers in the early 2000s already gave some geochemical and isotopic information which related it to a similar composition to the Anaga Massif. And then what we do know is that there is a very intense seismicity in this area, but this is normal because it's located in the middle of a reverse fault between the islands. So the seismicity is within normal levels, but sometimes it appears in the news. Apart from this, we don't know much more other than there have been some species that have been found at Enmedio volcano for the first time in the Canary Islands. For example, some species of bryozoa. One of them was even given the name of Acorania enmediensis. And also some ketognaths, which were actually derived from the Volcana project, these results. But this is pretty much all we know. So we are going to present a study that is supported in 3 different areas, like a stool supported by 3 legs. So one is the geomorphology, another one is the petrology and geochemistry, and another one is the oceanographic conditions surrounding this volcano from different perspectives, physical, chemical, and biological. Keep in mind that I'm an oceanographer, I'm not a geologist, so I will do my best to summarize the geological part, but this is this is my expertise, really. Okay, so here I summarize the methods that we used, but I won't go into too much detail. We used for the geomorphology multi-beam echo sounder for the bathymetric data, and also some sub-bottom profilers with topaz. For petrology, we did some towed dredges in the area, and those rock samples were analyzed with a lot of different techniques, different types of microscopy, X-ray fluorescence, mass spectrometry, stable isotopes, etc. And then for the oceanographic part, we sampled the area with an oceanographic rosette equipped with a CTD sensor, conductivity, temperature, and depth, and also a turbidity sensor. And we also took water samples, which were analyzed for the concentration of inorganic nutrients, and also cytometry for the prokaryotic abundance. But let's jump into the results. So first, the geomorphologic description. I'm just going to give a very general overview. The main cone has a fairly conical shape, with the only exception of a fracture or a fault zone here right in the middle of the summit, and a depression in the shape of a half moon on the southwestern flank. But then, as I mentioned, there are also many other smaller cones surrounding this volcano, between 10 and 20. At least 5 of them have a depression in the shape of a crater. They all have different erosion degrees, which is a sign of a long volcanic history in this area. And the 2 closest little cones are the most interesting ones. They also present collapse scarps, the same as Enmedio here in the depression. We also have some backscatter data, which just a general overview. We see different values of backscatter in the cones, especially in some areas, compared to the rest of the seafloor. This could indicate some rock alteration, maybe by hydrothermal activity. Okay, moving on to the petrology. I'm just going to show a little bit here, so sorry, José Antonio. One of the towed dredges that we conducted were passing through the main volcanic cone, and here we collected some rock samples, and they look like this. So they are altered in surface, and they have these yellow, orange, red colors, which are caused by iron deposits or hydroxide iron deposits. These are very typical of hydrothermal environments. They are very well described in literature. And then also, if we look at these samples in backscatter electron microscopy, we can see these filaments that are like, they have a very characteristic shape, and these are also very well described. They are biogenic iron-rich filaments, where usually there are some iron oxidizing bacteria that are typical of low temperature hydrothermal deposits. So this is already another clue. And now we get to the to our favorite part. To measure the oceanographic conditions surrounding Enmedio volcano, above the volcano, like I said, we carried out some sampling. Here you can see the bathymetry of the volcano, and here's where we sampled with a CTD and turbidity sensors. And so we obtain different parameters. So for example, here we have different physical parameters with depth. So these are vertical profiles carried out in the summit, in the half moon depression, and in the two closest smaller volcanic cones. And for example, here we have the first parameter is the turbidity. Turbidity in the ocean is usually quite low, around 0.2 NTUs, as you can see in the reference profile. The black line here is a reference profile. And what you can see in the samples in the volcano is that there are a lot of turbidity anomalies. Here it reaches 0.6, but in other samplings we reach even 2 NTUs. So this is a 10 times increase respect to normal conditions. Then we also have a parameter called the Bloom-Vaisala frequency that Juan Pablo already introduced before. So this is basically an indicative of the water column stability. So what this means is that if the water column is stable, this is calculated mostly by density, this parameter should be 0 under normal conditions. So what we see is that it's actually 0 everywhere except in the thermocline, that's normal, but it's always 0. And then when we reach this depth range, which is the depth range of the volcano between 1,600 meters to 2,200 meters or something like that, we start seeing a lot of alterations in this parameter, which is showing us that there is instability in the water column. So the water parcels are moving up or down because of density anomalies. And now if we make a zoom here, so this is to see the temperature, we're going to make a zoom and we see it from 1,500 to 2,200 meters depth. We can see the temperature in a profile of the temperature. In black, we have the reference profile. So this is the normal temperature in this area. We have 2 reference profiles. The darkest one is from CTD data, in situ data, right outside of the volcano. And then the lighter gray one is a climatological reference profile from satellite data from over 20 years. So what this is showing us is the maximum variation in this area over 20 years. And then in colors, we have the sampling at the volcano, and what we see is the temperature goes outside of both of those references, the CTD and the satellite references. So temperature is very anomalous. There are increases of up to 0.53 degrees. This is a lot in the ocean, especially so deep, where normal temperatures are very low. And an interesting thing is that you can also see a few negative anomalies. This can seem counterintuitive, but actually it's very normal in hydrothermal environments, because as we saw before, there is vertical instability. So there are several processes of vertical mixing happening, like entrainment of ambient seawater, or even cellular convection, or different phenomena. So this makes it seem like there is negative anomalies of temperature, but it's just because the water column is trying to re-stabilize. Then moving on to a more chemical oceanography, we also measure the concentration of inorganic nutrients, silicate, phosphate, nitrate, and ammonium. Here you see a reference profile always in black with standard deviation, and then in colors the samples we took at the volcano. So there are positive anomalies in all the nutrients, also some negatives for the same reason, because of the vertical mixing, but mostly positive. So silicate, for example, was 8% higher than normal conditions. Phosphate was 3%, nitrate 4%, and ammonium 437% more than normal conditions. As you can see here, all these points. So this is very high, and this is actually a very characteristic aspect of hydrothermal events, because ammonium is a reduced form of nitrogen, and the volcano emits the chemical compounds in a reduced form. So this is like a chemical signature of hydrothermal emissions. And then finally, we have just a little bit of biological information, microbiological. So from the water samples, we measured the prokaryotic abundance in the range of between 1,700 and 1,900 meters. And what we see is a generally higher abundance. Sorry, this is in gray, there is outside of the volcano, and in yellow is inside of the volcano. So we see generally a higher abundance, but it's almost significant, but not quite. Why? Because there's also a very high variability. And then another interesting thing that we see is that when we measure the percentage of high nucleic acid content cells. What does this mean? This means cells that are more active, more metabolically active. We see that there's actually a decrease. There is more abundance, but they seem to be less active. This is not very normal. So our hypothesis with this is that there are actually different communities. There are different microbial communities outside and inside of the volcano, and that's why we see different signatures. But of course, this is just the first hint. We have to do a specific biological study to see what's really going on. This is just one first hint. So to conclude, we already have the 3 legs of our stool. We have seen some geomorphologic data, petrologic alteration, and oceanographic anomalies in the water column from different. These are all different parameters, very independent from each other, and they all give us clues that there is something going on, that there is hydrothermal activity. So we feel confident enough to affirm that there are hydrothermal emissions at Enmedio volcano. And now, if you allow me, I will make a very brief summary in Spanish. Voy a hacer un resumen muy rápido en español, ¿vale? Hemos presentado un estudio bastante multidisciplinar en el volcán de Enmedio, entre las islas de Gran Canaria y Tenerife, en el que hay distintos indicios de que hay actividad hidrotermal en este volcán. Nos hemos basado en indicios tanto geomorfológicos de las estructuras volcánicas que hay en esta zona, también en petrología y geoquímica. Sobre todo he mostrado pues, que hay rocas alteradas con una, con una composición y efecto muy característico de salidas hidrotermales. Y luego hemos mostrado datos oceanográficos, es decir, en la columna de agua, en el ambiente marino alrededor del volcán de Enmedio, desde distintos ámbitos, es decir, oceanografía física, química, biológica, en los que también vemos anomalías que son características de ambientes hidrotermales. Por lo tanto, pues podemos afirmar que efectivamente parece que hay actividad hidrotermal en este volcán profundo. Eso es todo. That's all. Thank you so much. Bueno, continuamos. Sorry, we're going to continue with Jesús Alcázar. Jesús is a marine biologist, and he holds a PhD in biodiversity and conservation from the University of La Laguna. His research focuses on soundscapes, working in projects that involve the biological, anthropogenic, and geological branches of marine acoustics. He has published research regarding the acoustic behavior of deep diving cetaceans, such as big whales in the Canary Islands. And he's also worked in projects combining active and passive acoustics to study the mesopelagic diel vertical migration that fishes like some myctophytes undergo at its sunset and sunrise. And currently, he's a postdoctoral fellow from the University of La Laguna, and he was here with us for 2 years as well in the Spanish Institute of Oceanography, investigating soundscapes around submarine volcanoes in the Canary Islands. Great professional. So go ahead, Jesus.
Thank you so much, Alba. And well, thank you to the organizers for having me here. I miss you all. So yeah, I'm happy to be here. So I'm going to talk to you about, well, here on behalf of all the co-authors, a paper we have just sent about hydroacoustic detection of volcanotectonic seismicity during the Tajogaite eruption in La Palma. Okay, since I am assuming we are not all seismologists, for example, I'm a biologist, we are starting with a brief tale of seismic sensing. So when there's an earthquake, we use seismometers on land to detect it. So basically are accelerometers. And this is the typical high school geology diagram for the propagation of earthquakes. What you detect is a primary or P wave and a secondary or S wave. And you can see here that it propagates through the crust, but the S wave do not like the fluids, so only the P waves propagate through fluids. But what happens if there is an ocean in between the earthquake and your sensor? Some studies have demonstrated that this P wave, the primary one, once it encounters the seawater, it is transformed from a seismic wave to an acoustic wave, and it can travel through this SOFAR channel that is located some 1,000 meters depth, and it travels teleseismic distances until it meets again the crust, and it's converted into a seismic wave that can be detected in your accelerometer. So this has been demonstrated, and it's called the tertiary or T wave. This is an example of an earthquake that occurred in the Greenland Sea, and it was detected in the west coast of Norway by an on-land seismometer that detected obviously the waves that travel through the crust, or the primary and secondary waves, and then some minutes later, since the T wave travels slower in the water, this tertiary wave. Okay, so some researchers wondered, could we measure or identify this T wave in the water? And we can. Here's an example of an earthquake that occurred in Brava in Cape Verde. This was recorded in their on-land sensors, the P and the S wave that was also detected in the Fogo Island, and then in a hydrophone in the oceanic rift that was floating at this SOFAR channel. It was only detected this T wave. Okay, so now we have another seismic sensing method, which are hydrophones detecting T waves. And it's not really common. And what would happen if we place these hydrophones directly on the seabed? Well, this was tried in Italy, and they collocated hydrophones with a seismic sensor directly on the seabed. And they saw that the hydrophone acted as an accelerometer, so it recorded the P wave almost equally as the seismic sensor. So it was acting as an accelerometer. Okay, so bear in mind these two sensing methods that we'll use later. Luckily, some people have already talked about La Palma eruption, so I can go briefly through this. The lava flows reached the sea, and the Spanish Oceanographic Institute was there, was taking samples from different disciplines, and always also from acoustic perspective. So there was a hydrophone mooring there during the eruption and 1 year after. So what we are going to look here is to investigate the possible changes in the marine soundscape while the volcanotectonic seismicity was taking place. Okay, so here we have the map, La Palma, the volcanic vent, the lava flows, the lava deltas, and also the hydrophone mooring that was within a marine reserve. And we studied 3 different scenarios. So during the eruption, with our vessel working nearby, then 1 year after the eruption with our vessel working nearby, and then without the vessel. Okay, and please look at our 3 deployments where the hydrophone was located floating above the seafloor from 2 to 3 meters floating in a water column of some 80 meters depth. Okay, this was for the first and second deployments, and in the third one, the hydrophone was directly resting on the seafloor. Then we asked our colleagues from the IGN, the Instituto Geográfico Nacional, about their earthquake catalog. So they let us this data. In here, the circles, you can see the blue ones correspond to the earthquakes that took place while we were in our first deployment, and the orange one, those that happened in the second and third deployment. Okay, and in the red squares, you have all the IGN seismic platforms. So going to our acoustic analysis, we used MATLAB and Audacity. First, we calculated overall soundscape matrix. I'm not boring you with the details, but these were the 3rd octave band levels, which roughly means that we were calculating the sound levels for some specific frequency bands. And then we performed an oral exploration. We were seeing spectrograms at low frequencies, following bibliography, where they say that most of the geophonies occur at these low frequencies. And then the signals that we encounter, we characterize their waveform, their frequency component, and its sound levels and intervals. And then we compare those with seismic detections. And let's see the results. Quite interesting. This, for start, is the overall soundscape matrix. What we are seeing here, don't panic, are in the x-axis, the 1/3 octave bands. This just means that here we have the hertz, like this is at 10 hertz, at 100 hertz, at 1000 hertz, okay? And then in the y-axis, we have these sound levels in decibels relative to 1 micropascal. These are all acoustic terminology, and the colors are indicating these 3 different scenarios. So in red, we have during the eruption with the vessel working. In blue, 1 year after the eruption with the vessel, and in purple, 1 year after the eruption. Okay, and if we focus on the most striking part, the low frequency, we see a clear differentiation with during the eruption and 1 year after the eruption. And please, you have to bear in mind that the dB scale is a logarithmic scale. So this 13 dB difference is just colossal. So we wanted to explore this low frequency to see what was happening. And if we look at these spectrograms, we started to see these spikes, okay? So these were some signals that we wanted to explore. We wanted to see if these were some kind of anthropic impulses, maybe for seismic exploration or something like that. So we first looked at their intervals between signals and also their apparent source level. And as you can see, this like natural randomness pointed to a natural source and not an anthropic one. So we went picking all of those signals that we could see and characterize them. And what we found, was this. First, in the waveform, we saw that actually each signal was made up of 2 pulses that were separated by a very, very stable interpulse intervals of some 2.6 seconds. Then looking at the frequency component in the spectrogram, we saw that the first pulse had always a center frequency around 15 hertz, and then the second pulse, it was more diffuse and had two peaks, one at some 6 and the other at 12 hertz. And also we saw that it was quite a quick rise time for the signal. And we also look if those two pulses were related, where they were obviously related, and we could see that the first pulse of the sound levels of the first pulse influenced the second pulse sound levels. Okay, so those were related, and we have a bunch of these signals in our recordings. And then we asked again our colleagues from the Instituto Geográfico Nacional, okay, so we know there were earthquakes, but we wanted to see the actual raw data from your accelerometers. So give us some example, please. Okay, sure, you have here. So here the seismic detection in time and the velocity, and we say, okay, we are going to see the same date, the same minute. We have a time lag problem, but we corrected it. So in our recordings, we had this. And if we superpose them, they are quite similar, right? And we said, okay, let's go through all of our signal detections in the acoustic records with this totally independent data and see if there were seismic detections. And this is what we got. So the blue circle is this detection, and the gray ones are all of them. So we ended up with 712 underwater acoustic detections of volcanotectonic earthquakes, which we weren't expecting. And just remember that we were detecting them 7 kilometers from the volcanic vent, and the other sensor with independent data was almost 12 kilometers away. And we also had an apparent magnitude threshold for detecting acoustically these earthquakes at 1.9. So at magnitudes of less than 1.9, we didn't detect anything. And this is one of the explanations why we don't have any detection of these earthquakes 1 year after the eruption, because none of them were of greater magnitudes than 1.9. And this is what we are proposing now to expand the seismic vigilance of La Palma, but also the other islands, to help these seismic stations with hydrophones. Okay, because the islands have a limited area, but we could help this localization of earthquakes by simply deploying hydrophones, but we must coordinate all of these with GPS so the clock is exact. Okay, and here, graphic design is my passion, as you can see. Just to recapitulate the hydroacoustic seismic sensing methods that we have. The first one is, remember, if we deploy a hydrophone floating at some 1,000 meters depth, we could detect the T waves. Okay, this normally happens really far away from the source. And this, yeah, you could use it for seismic detection and also soundscape characterization, but it's not really so useful because this is really costly. Then we have another method of deploying the hydrophone directly on the seabed. We could detect earthquakes since it is acting as an accelerometer, but we could use it for nothing more because for soundscape measurements, this is no good. But now, thanks to La Palma, we have a new one, a new detective method that is a floating hydrophone at least 2 to 3 meters above the seabed, and it is floating at 77 meters depth. That it is allowing us to take in soundscape measurements. We also were detecting, this is another talk, fish, whales, dolphins, but at the same time, we were able to detect quite precisely the P and the S waves, which is quite new because we were so near the seabed without being resting on the seabed that allowed us to do this. Okay, and then we also wonder, could we predict the volcanotectonic earthquake magnitude using the received sound levels in our hydrophone. And we could. Here you have the scatter plots for the earthquake magnitude and the sound levels for the first signal and the second signals. And we could use either one of them. So if we have, say, 120 decibels, we go here and we have roughly some 4 magnitude earthquake. So this is new for this configuration, so great. And also this works backwards. So if we had all this information from the Spanish Geographical Institute of all the earthquake magnitudes, we could even go further, this is a next step, and estimate how much geological noise La Palma was giving to the surrounding sea. And just to conclude, so yeah, we were performing hydroacoustic seismic sensing close to the seabed. We have demonstrated with many of these earthquakes. This is quite new. We are super happy about it. You have here how well this works. And even more, the sound levels allow us to correlate with seismic magnitude and backwards. And yeah, we have demonstrated for the first time how a subaerial volcano and its related seismicity affects the marine soundscape. And remember, we were in a marine protected area. And this highlights the importance of this passive acoustic monitoring to study these areas of difficult access or potentially dangerous, as it was previously said of drones, but this is better. And we are proposing to expand the seismic monitoring of the Canary Islands through this coordinated effort between disciplines. So thank you.
Thank you so much, Jesus. It's really interesting to expand the seismic vigilance network into the marine realm. So next we have Eduard Puig Muntellà. He got his bachelor's degree in civil engineering from the Polytechnic University of Catalonia. And in 2016, he began a joint PhD between this university and the Grenoble University. Alpes University. His research allowed him to develop and improve numerical tools for studying unsaturated granular media on a small scale. In 2020, he joined the Laboratory of Geophysics and Industrial Flows in Grenoble and as a postdoctoral researcher. And during this period, he also worked on implementing new numerical techniques to study sediment transport. And he has recently joined us here at the Canary Islands Oceanographic Center to carry out the NULACAN project, numerical investigation of landslides and tsunamis in the Canary Islands. Really interesting research. This project is funded by a Marie Sklodowska-Curie postdoctoral fellowship program. And his project aims to reduce these uncertainties that there are through simulations and analysis of submarine and subaerial landslides, improving risk assessments for landslides and tsunamis in the Canary Islands. We are very glad to have him in our team, so go ahead.
Thank you, Alba. Okay, so today I'll talk about different numerical approaches that are used to model landslides or the tsunamis that are generated by these landslides once they hit the ocean or a big lake or other large bodies of water. So the key in numerical modeling is choosing the right model depending on the phenomenon we want to study. For instance, if we are interested in having a better understanding of the triggering mechanisms of landslides, then we have to look at the microscale, like here, and model the particles and the interaction between particles. Instead, if we are more interested in modeling the evolution or how these landslides develop, or also how these landslides impact obstacles like buildings or other structures, then we have to rely on mesoscale approach, where we have to resolve 3D Navier-Stokes equation. And finally, if we're interested in very large landslides or wave propagation in tsunamis or turbidity currents, then we have to adopt a macro scale approach. And then we have to simplify the physics of the problem so we can reduce the computational resource, the computational time. The idea I'm trying to make in this slide is that as we go to larger scale, our models usually become less detailed, but at the same time, we adopt computationally more efficient methods. So in this presentation, I will try to cover this wide range of scales. We'll start at the micro scale. In this case, we're going to use the DEM, which stands for discrete element method, and we are following each particle. So we are modeling the interaction between the different particles, and while we fully resolve the fluid around these particles. So these methods are excellent if we want to study the physical phenomena like I don't know, cohesion, fluidization, the origin of turbulence, things like this. But the problem is that they come with a very computational cost. So you can usually not go beyond the meter scale. So usually you model something like this big, so relatively small. And then we can go a bit further up in this diagram. So we can use multi-phase Eulerian approach. So in this case, we are no longer following each particle. So instead, we are using Eulerian approach. That means then that we are averaging the quantities like pressure or velocity or porosity. And we solve the Navier-Stokes equation in 3D for both the fluid and the particle phase. And that allows us to model certain practical cases like erosion around a structure or the migration of dunes or how these landslides develop. So the application range in this case is between 1 and 20 or 50 meters. And finally, if we go to the other end of this spectrum here, then we have the depth average models. So we still resolve the Navier-Stokes equation, but we get rid of one dimension, so we don't solve on the vertical direction. So it's much easier, but it's less accurate. So in this case, we can model some phenomena that are beyond 100 meters or kilometers. Things like this. Examples are turbidity currents, also lava flows in horizontal planes, morphological changes in the beach, etc. So before I go any further, I'd like to say a few words on two types of soil failure that depend on the initial compaction state. So let's start with the loose granular material like this one. So when there's an episode of intense rainfall, what happens is the water infiltrates in the soil, and then there's a buildup of pore pressure that weakens the soil. So the soil is more prone to fail, like showcase here. So it collapses. This is an episode that is very rapid, so it lasts just a few seconds and can have devastating consequences. And in the dense case, something very interesting is happening. Please try to stay with me because it's a bit complex. So we have this situation. So it's a dense sandy soil under the water. And this situation is out of equilibrium because here we have a very steep slope. And that means that the material that is right over here wants to move down because of gravity. And because of that, there's shearing deformations, and that causes some expansion of the granular material. I will explain it a bit better in the next slide. So because of this expansion, we are creating new pore space. So there's a fluid flow that goes from the outside towards the inside of the granular material. That induces some negative pore pressure that increases the strength of the soil. But at the same time, because it's expanding, the particles that are really close to the front, they tend to be pulled down by gravity, and they are released. So they form a turbidity current like this one, and this front recedes like slowly. So for instance, in this case, we have an aerial photograph that was taken 2 weeks apart. So you can see that this type of failure can take up to days or weeks, but it can also affect the surrounding infrastructure. Okay, so the concept that help us understand these two different behaviors is the latency. So now we have to zoom in at the microscale. And what we have is, in a loose case, we have this, no, I don't know. Okay, so at the microscale, we have this scenario in the loose case. So when we start shooting, the particles reorganize themselves, occupying the empty space, like here. So there's an overall contraction of the granular material, and the fluid is expelled from the inside, so it flows outwards, and that creates a positive pore pressure that reduces the strength of the soil. In the dense case, not very surprisingly, we have the opposite scenario. So at the beginning, we start with a very compacted state, and then we start moving, and they rearrange themselves. So we are creating new pore space. So the fluid flows towards the empty space. So there's negative pore pressure that increases the strength of the soil. So now we can perform numerical simulations at the microscale. So we are, in this case, we have a granular assembly that we shoot it. So we apply a force like this, a tangential force. And what we see is that this red line indicates the height of the sample, and it increases. And also you can see in this plot that the material is expanding, and we finally reach an equilibrium. And we can gather all this information to improve our models at the mesoscale. So we don't really have to solve all the interactions, because here we are solving everything, but this is computationally very expensive. So from now on, we are not going to use Lagrangian models. That's the previous one. So where we were following each particle. So instead, we are going to consider Euler models. So here we're averaging every quantity. For instance, here I have the porosity, the opposite of porosity, but the solid volume fraction. So that means that we have, for each cell, 60% of granular material, 40% of water. Here, for instance, when there's zeros, that means we only have water. So we are solving Navier-Stokes equations for each of these cells. So don't be overwhelmed by this amount of equations. I'm not going to go over them. But the idea is that because of that simulation that I was showing you before with the particles, so we can get enough information to write down a mathematical formulation for dilatancy model that can actually model the dilatancy instead of solving it. So it's computationally much more efficient. So we're going to test our dilatancy model with this experiment. So this is a granular collapse. In this experiment, we have a tank filled with water. Then they place a vertical gate like this. And on the left side, we have granular material. So we start with two different initial cases, a dense material and a loose material. And they observe that for the dense case, the material was moving very slowly, while in the loose case, the collapse was very, very, very rapid. So this is our numerical simulation. So we'll start with the dense case, and you can see that it takes a while, but it starts moving. And we also see some expansion. It goes from these dark orange colors to these pale orangish colors. And it takes around 10 seconds to finish. While for the loose case, the collapse is very, very rapid. And just in a few seconds, we end the simulation. So we can compare our numerical results with the experiments. You can see the experiments here are represented with these dots. So you can see that by the end of the simulation, we have this S shape for the dense case, while for the loose case, it looks more like a triangular shape. But in both cases, there's good agreement between our numerical approach and the experiments. And because we're using numerical model, we can have access to all the local data we want. So for instance, we can map the pore pressure. So you can see that for the dense case, the negative pore pressure develops within the granular material. That means that we increase the strength of the soil. That was the reason the motion was delayed. While for the loose case, we have this area in which we have positive pore pressure. And that area actually it corresponds to the shear failure line. So there's in this area, the pore pressure increases. So it's kind of fluidized. So the collapse occurs right above this line. Okay, so now we can add, we can go one step further and include the presence of the free surface. So we have a submarine landslide that started here, and that created a a perturbation on the free surface. And this kind of, well, I started this 2 weeks ago, so I don't have lots of results. But the idea is that we can use this type of simulations to study the wave generation mechanism, also to study the role of pore pressure beneath the granular material, because it's been reported that the turbidity currents can travel for hundreds or thousands of kilometers, and probably free pressure underneath plays a very key role. And another idea we've got is to reproduce the Tagoro landslide and the perturbations that were created on the free surface. What else? So we can also place the origin of the landslide right above the seabed. So here we can study other phenomena like the role of air that is entrapped inside the granular material. It's not the same of having a big boulder or a chunk of solid rock that falls into the ocean, that having a lava flow or having a very deformable granular flow. In those three cases, the dissipation is very different. So with this type of simulation, we can study what will happen in different scenarios. And in previous cases, I was showing you what happened in a very ideal geometry, like an inclined plane. Now let's see what happens when we have something a bit more real. So we're going to place ourselves in El Hierro, more specifically in Las Playas, where we have this collapsed scarp here that happened 150,000 years ago. And still you can see that it has very steep slopes. And here we're going to perform a landslide that has its origin right here, or a rockfall. And you can see that the debris material takes a preferential path, and eventually it reaches in this area that corresponds to a milder slope, and then it settles there. So this simulation actually took forever because we're solving everything. So we're solving the 3 direction, and then here it's kind of difficult to see because the mesh is everywhere. So there's just a plane that cuts everything. So you can see that the mesh is actually very coarse. That means that it's not very good. And even with that, it took 1 week to run in one personal computer. So it's a lot of time. And it's an alternative. What we can do is to run a depth average simulation. So in this case, we don't solve on the vertical direction. So we simplify the physics, but in this case, you can run a very similar simulation, but only with 1 hour. So this is an example of, it's not exactly the same simulation, so please don't compare it, but the idea is that you can run the same type of simulation much faster. And again, the debris material stops in a very close area, also where we have this mild slope. Okay, that brings me to the end. 3 main take-home messages here. The micro-scale approach can be used either to have a better understanding of the physics at the microscale, or also to improve or to upscale other methods at the meso or the macroscale. We can use mesoscale if we have the computational resources for studying, for instance, the impact on obstacles, or to study how a landslide can develop, or what's the preferential path of a lava flow or a granular flow. And finally, for macro scale models are a great tool if we're more interested in having mapping the different risks, or if you want a very rapid response. And that would be all. Thank you.
Thank you so much, Eduard. I think your research is going to be very important for the Canary Islands in general. So now, I mentioned before that Vulcana supports young professionals, but I should mention that GeoTenerife also is very passionate about this, and is always supporting very young and talented people. So now we're going to see one example. We are going to listen to Javier Díaz Cabrera. He's a master's student. He's from Gran Canaria, and he studies meteorology and geophysics at the University of Granada. He graduated in environmental science at the University of Stirling in Scotland, And he's interested in emergency management, especially in the Canary Islands, and he's here as an intern from GeoTenerife. Thank you, Javier.
Okay, thank you so much. I also want to thank Sharon for encouraging me to participate today. Today I'm going to be speaking about a pilot study which we conducted during this summer's GeoIntern program, in which we studied volcanic readiness in Vilaflor. So this is just a brief outline of what I'll be talking about. Like, I'll be introducing everything, why we're doing this, the methodology we followed, our results, a discussion, and some recommendations that we made from our research. So firstly, this is everything that Alba has already said. Just what I've been doing. I've done a degree at the University of Stirling. Then this summer, I participated in the GeoIntern program. And this autumn, I've just started a master's degree in meteorology and geophysics at the University of Granada. So most of you will ask, what is GeoTenerife and what is the GeoIntern program? Well, this is a program prepared for early career researchers, which really focuses on science communication, extensive field work, and you also get a lot of time with local experts. And the good thing is that the results that you produce are actually used in the Volcano Stories project. So why study volcanic readiness in Tenerife and specifically in Vilaflor? Well, to begin with, we have in Tenerife a large resident population, but we also have a lot of tourists. So if we sum this up with the fact that we have explosive, effusive, and hydrovolcanic volcanism in Tenerife, the result is that we have a really complex emergency setting. And why did we study Vilaflor? Well, firstly, it was located in close proximity to where we stayed during summer. Then we also thought that it would be a representative example that could be applied elsewhere in the Canary Islands. We also thought that the fact that Vilaflor had an aging population would be interesting when it comes to evacuations and emergency management. And we also went to Vilaflor because it's a small town, and we thought that we could really listen to everyone and get in contact with the people, because how are you going to manage an emergency without knowing who the people are and who you're working with? So regarding the methodology, the first thing we did was a buildings and infrastructure survey. So we walked throughout Vilaflor, looking at roof types, the age of the buildings, and how they were constructed. We also conducted a residence survey in which we also walked through Vilaflor, asking residents a questionnaire of 15 questions that was designed to be of short duration, so we made sure that everyone answered all of the questions. And we also set up a table in the middle of Vilaflor so that residents could come and complete the surveys. And finally, we also spoke to representative figures in Vilaflor. So, for example, the mayor of Vilaflor, the local police, the BRIFOR captain. The BRIFOR are the Brigada Forestal, which are the forest firefighters here in Tenerife, and we also spoke to the staff from the school summer camp. So what were our results? Well, to begin with, we saw that over 60% of the buildings in Vilaflor had flat roofs, and we also saw that a considerable amount of buildings were old and were built before 1930. When it comes to the resident survey, we saw that 60% of the people were aged between 35 and 54 years. However, we also saw that a significant portion of the people were aged over 70. It's also noteworthy to see that 56% of people moved by car. So you see that people are dependent on cars in Vilaflor. And finally, we also thought that was interesting that almost 30% of households said that they would require assistance in the case of an evacuation. We also Amongst other questions, we also found out that 84.3% of the people felt uninformed by authorities regarding volcanic hazards. We also saw that when it comes to obtaining this information, people trusted the most the local town hall and the police. But what was the most interesting was that only 1.7 answered that that they thought of scientists as a reliable source of information. We also found out that the majority of the people felt either very unconfident, or not sure on the accuracy of updates that they would be provided with during an emergency by the local authorities. When speaking to the figureheads in the community, obviously I would like to thank all of them for spending some time to speak with us. For example, Agustina Beltrancano, the mayor of Vilaflor, said that she really wanted to see a consolidated discourse between the IGN, the Involcan, and CSIC when it came to volcanic hazards and emergency management. And she also mentioned that during an emergency, who the people trust the most are the army and the police, because they view the army and the police, they see them in person working with them. And for example, with scientists, as they're not in person with them, they don't trust them as much, or they can't rely in them as much. Then, while speaking to Carlos Viloria, the local policeman, and Miguel Angel, the captain of the firefighters, both of them said that they were very understaffed. So in the case of an emergency, the first thing they would have to do is contact policemen and firefighters from other municipalities to come and help in Vilaflor. Another thing that we found really interesting was that Carlos Viloria said that during an emergency or an evacuation, they depended on loudspeakers to conduct an evacuation. So if you think about it, if you're living on the fringes of Vilaflor, it's quite possible that you might not hear the loudspeakers. So what will you do in this situation? Hopefully you will hear it. So what do all of these results mean? Well, having such a large proportion of flat roof buildings is a problem, because if you have a volcanic event, you're going to have intense ashfall. And what ends up happening is that the accumulation of ashfall on the buildings can result in their collapse. While walking through Vilaflor, we also saw that many of the streets were really narrow, as you can see. So you have a parked car, and maybe another car can go through this space. And basically, the issue with this is that during an evacuation, this makes the evacuation effort much more complex. Also, if we take into account that people in Vilaflor are dependent on their cars, well, you can expect to have congestion or even accidents during an evacuation. When it comes to demographics, as I said before, we've seen that there's a really that there's a significant elderly population in Vilaflor, and this is a real issue because during an evacuation or an emergency, taking care of these elderly people is much more complex than handling a younger population. And also, we found out that it's really useful to have a single discourse during an emergency. So in this way, people won't receive different informations, and they have one single discourse that they can really understand. If they have some people saying X stuff and other people saying Y stuff, they're going to get confused, and it's going to be much more difficult to do any kind of evacuation. And finally, what we also saw that was really beneficial was having a periodic interaction between the population and the scientists to build this bond between them. So, having produced this pilot study, we also thought that we could offer some recommendations. So, the first thing that we thought was really interesting was that a lot of the respondents were used to or knew about forest fire hazards. And we thought that informing them about volcanic hazards through forest fire hazards was a viable option because, for example, if you have a lava flow coming into Vilaflor, that can be explained in the same way as having a forest fire front coming into Vilaflor. Then we also thought that scientists need to increase the engagement with communities. Also, going back to the beginning of my presentation, there's a lot of tourists in Tenerife, so we also would need to produce evacuation plans and any kind of information that we produce in English or even in other languages. Thinking about the aging population in Vilaflor, we also need to think about how we provide them with this information. So we need to make this information much more accessible. So for example, with the use of pictograms for people that can't read, etc. And finally, what we thought would be really useful, as there's still people that might not have access to social media or the internet, was to provide written information, because maybe in the case of an emergency, there's a loss of mobile data, and you always can fall back on the written instructions that you might have on your fridge or something like that. And linked to this, we decided to produce these exemplar pamphlets where we include information on the forest fire hazards and the volcanic hazards. So in this way, the population have all the set of the information, and then they can also make comparisons between both things. And for example, maybe these pamphlets, they can just stick it on their fridge and forget about it, but when they really need it, they're always going to have it there. And yeah, thank you so much for listening, and thank you so much to my fellow colleagues, Isabel, Jack, Brooke, Carmen, and Wisdom, that took part with me during this pilot study. Thank you so much.
Thank you so much, Javier. That was really interesting, really great work. Now we're going to have the Q&A session and general discussion with all the speakers. So if you could join us here. We are quite a lot of speakers this time. But
if you'd all like to come to the front, that would help me so I'm not running up and down the steps.
Yeah.
I'd love to say thank you very much to all the young career and early career scientists who took part in this session. Eugenio, I have to say this is my favorite session that we run at VulcanaSymposium. The depths of science that's done here is incredible. The fact that these young scientists are working on a range of different subjects just shows you the depth of science that is being done in the Canary Islands. And there's an almost unlimited amount of science that can be done. These islands are incredible, and there's still so much that we don't know. Volcanology is a very early, young science, and we need a multidisciplinary approach. And this is what Eugenio does so brilliantly in Vulcana. You know, he brings people in from lots of different backgrounds. If you have the wonderful opportunity to go on his research vessel, you won't just see marine biologists on that vessel. And that's beautiful. They all work together, they all collaborate, they all communicate, they all share. And that's what we need so much more of in science. If I can just have a very short incision here, we have brought hundreds and thousands of young scientists to the Canary Islands over the past 13 years, ironically. I think we started about the same time. And it's not always that experience that they have when they start out in their careers in science, and that's really shocking. We have collaborated, we have linked up now with American Parity in the United States, because we are very conscious that bullying and other unacceptable behaviors are still a part of science, particularly in the early years when scientists are not able to sort of perhaps voice their concerns, or they feel they don't have a platform from which to defend themselves. We have started a Stop Science Bullying campaign, and anybody who's interested can go onto our website. There's a link there, and you can fill in a form. I encourage everybody, please, if you can and would like to fill in the form and then share it, because we're trying to get a grasp of how widely these things are happening. And some of the stories we've heard are truly shocking. And some people are so marked by what's happened to them, they don't feel they can actually fill in the form. They don't know where to start. And this is a side of science that I think we need to talk about. So first of all, we're trying to quantify how widespread this is, and then secondly, try and see what resources are out there, what's available, how we can support and how we can do better. And I think it's a real testament to this whole Volcano program. First of all, how confidently all these young scientists stood up and spoke. Alba, I've known you for years and you are amazing. You were amazing back then, but you keep just growing, and I think it's fantastic. And the fact that Eugenio has developed this in order to promote his young scientists, to have a platform, to be able to talk and to present. That's not always the case in science groups, and I'm sure you know that far better than me, where some people perhaps like to have more protagonism than others. But anyway, that's enough from me, and I would like to open the floor to any questions you guys might have. Rama, if you'd like to tell us who you are.
Hi, I'm Rama. I just graduated from the University of Birmingham in the UK. And I'm a wannabe volcanologist, so I'm back doing Marine Sci Camp because I want to learn a bit about submarine volcanoes. I have a question for Scott. Does the submarine have any instruments for like in situ elemental analysis, just so you don't have to worry about collecting as many samples, and especially for your space exploration, just because of the costs and the difficulty associated with sample returns?
Yes. So the submarine this is actually some stuff we learned from the Hawaii Undersea Research Lab. So we have a ambient temperature meter that's right in front of the viewports to ensure when we're doing temperature and gas samples that the submarine is safe. But then, yes, of course, we have CTD that can be hooked in to get the information either immediately or recorded, depending on what the scientist wants. And then as far as grabbing the data, we have temperature probes that are somewhat sacrificial because sometimes they turn black and die. And so we do have those, but then we currently don't have it's a pressurized gas and water sampler, so it keeps everything in the most pure form, but we have the ability to build it. So we're just waiting for a scientist to tell us that they need it, and we'll build it for them.
Build it and they will come.
Exactly.
Any more questions from the floor? Yes. Joe, tell us who you are and where you come from.
Hello, Joseph Smith from Kingston, Jamaica. I am GeoTenerife's lead social media coordinator and a former Geo intern at GeoTenerife. My question is for Javi. I was out there with you on some of the days when you were conducting these surveys in Villaflor, and I just wanted to know from you, what was a statistic that really took you by surprise, like something that you didn't necessarily expect to find out there doing these surveys with the locals, and that really, took you off guard?
I'd say, but than a statistic, the feeling that most of the people didn't think that an eruption other than from the main Teide Pico Viejo complex was possible. So, for example, people in Villaflor only thought that they might be affected by ashfall when there's many more hazards that could affect them, but they're not aware of this.
Thank you, Javi. That's absolutely right. And obviously, this is a pilot project at GeoTenerife. The whole point of trying to use our training programs and resources is to try and fill in some gaps. I don't think there's any groups here on the islands at the moment looking at these sort of subjects, and I think they're critical. I think emergency plans are amazing, but if you're not actually looking at the reality on the ground, and it's different if you're looking at Playa Las Americas or Santa Cruz or Villaflor, the reality on the ground is absolutely different. So this is a pilot study that we have done, but obviously we would love to be able to collaborate with the emergency department here and everything that's happening in order to widen this further. And I'd just like to pay credit to you, Javi. I don't think it's very easy at your stage in your career to stand up in a room full of scientists and tell them, people in Villaflor don't trust what they're saying right now. So I think that took a lot of courage, and it's a difficult message to hear. But now is the right time to hear it. There's no point thinking about this when things start to happen, when noise starts to get loud. Now is the time that we can do something about that. And that's something that we're going to be talking about at the end of the next session when I present. Any other questions from the floor? Yes.
Thank you very much. I have a question for Alba about the. Oh, my name is David. I'm from the Geological Survey of Spain, and because it's a volcano that I don't know nothing about him, I wanted to know if you know, because you talked about a reverse fault system that is. We are talking about a central volcano system or a monogenetic type of the region.
Oof, I think that's more of a question for geologists. I know that there's been a discussion about this. I've been reading lots of bibliography, and the fault between Gran Canaria and Tenerife has been an object of debate, but I don't know if I feel confident enough to answer. Maybe our colleague José Antonio could talk about this. Maybe it's a good opportunity to do it in Spanish, one question in Spanish. So if you could repeat in Spanish the question.
Vale, bueno, sí, que hablas acerca de un sistema de falla inversa. Entonces yo quería saber si sabemos si es un sistema, estamos hablando de un volcán asociado a un sistema central o a un sistema monogenético.
La única manera de saberlo es datando. Y no tenemos todavía datación de los diferentes tipos de rocas que hay ahí. Sabemos la geoquímica. Tenemos rocas muy diferenciadas de tipo fonotefrita, es altísimo. Y luego otras que son más comunes de las que tenemos aquí en Canarias, como la de La Palma, que son basanitas. Con lo cual pueden haber ocurrido una después de otra. Mientras no lo sepa la datación, pues no lo sabes.
Sí, realmente hay muy poca información sobre este volcán, por eso nos parece tan importante empezar a publicar sobre esto, porque ha sido el gran ignorado hasta ahora en la vulcanología submarina canaria.
Thank you, Alba. Yes, Ulf.
Thank you. Ulf Skyllberg from Sweden, northern Sweden. I think I have a question. I think it was Juan Pablo. You talked about the pH changes in connection to the hydrothermal vent in the Mediterranean Sea, was it? So these big pH changes also, Eugenio talked about that in connection to Togoro. Huh? What's the major source for this pH change? Is it the carbon dioxide or is it sulfur dioxide?
Yeah, thanks for your question. So this is a hydrothermal system where we found a lot of bubbling, and this bubbling was made of more than 90% of CO2, and also so that's one reason of this very low pH, and also the release of reduced compounds. We sample ammonium, but we also know that probably we have iron and other reduced compounds there.
Thank you. Nieves, I think you have a question. If you'd like to introduce yourself, you just push it in and hold it.
Now? But it is in green, but it's not in green. Sorry.
Hello.
Yes.
Hola.
I don't know. Just two questions in English or in Español? In English is great? Okay. So the first one is for José Antonio and Alba, just to speculate. Do you think the Enmedio volcano is now an active volcano under a kind of eruption or not? It's just to speculate, so don't worry about what you are going to answer. Just to give a big...
To me, with my limited knowledge of geology, but I do know a lot about hydrothermal systems, to me, right now, there doesn't seem to be any evidence of an upcoming eruption. I know that there's been activity lately, it's been in the news. Sometimes it seems like when it's in the news, it's stronger, but I think it's within normal levels. And the hydrothermal activity that we see is is present, but it's normal. It's the same that we see at Tagoro, for example. We don't have any clues that suggest that there's going to be an eruption for now. We don't know if this can change in the future, of course.
Okay, that was the question. No. So thank you. And the second one is just a comment on the presentation of Javier. It's really very interesting, but the problem is that some colleague of us has been doing during some time kind of talks with the population, and they tell us that many times they went to a village just to this night or tomorrow in 3 days we have a talk about hazards in, I don't know, just for conscientization to be people aware of the risks, and the room was absolutely empty. So sometimes it's difficult to achieve this reach to the population because population doesn't want to know sometimes. So it's just, again, to speculate.
Javi, if you don't mind, sorry, but I'll take that question. And I'd say you're absolutely right. And I think that's a very strongly held belief between a lot of scientists here. But there's a big difference between talking about science and doing science communication. So your local population doesn't want to have a lot of science stats thrown at them. And they do have an interest, and just the fact that quite a few of them have signed up to this symposium is interesting as well. I think a lot of them will be listening into this afternoon session, and it's absolutely something that we're going to be talking about in the afternoon session. How to engage local populations, because it's not just saying we have a chat about this and you must come because we know everything. It's also finding the way of how to engage them, how to get it in, how to have a discussion, how to infuse them. And it's important we have to have these conversations, because right now what we're finding in Tenerife is people don't know who to listen to, and that could have really serious consequences. And it's not because there isn't excellent science being done. There's some amazing science being done. But I just want to make sure people don't just listen to the loud voices, they listen to the good voices, and that those good voices cut through the noise. And that's what we're going to talk about later. Okay, anybody else? Yes.
Ok, thank you. En español para el profesor Lozano, ¿han hecho estudios comparativos, por ejemplo, my name is Alberto, I'm underwater archaeologist, I'm from humanities, but I'm here, and I would like to ask if there are comparative research between landscapes like Garachico with current landscapes like underwater en La Palma. Vamos, que si se han hecho estudios comparativos en poblaciones que hayan sufrido históricamente erupciones en áreas, es decir, para ver cómo se comporta la población en áreas pobladas y cómo, es decir, qué tipo de erupciones, voy a reformular. Se han estudiado los fondos de Garachico y partiendo de la reacción de la población de Garachico en 1706, ¿se puede establecer algún tipo de patrón?
Pues no te sabría decir. No te sabría decir, porque claro, la población de Garachico en esa época era un pueblo tan pequeño que comparado con lo que puede ocurrir a día de hoy en la isla de aquí de Tenerife, pues no es comparable. De todos modos, te digo, si tenemos en mente, eso mis compañeros geólogos de aquí lo saben, si tenemos en mente que el vulcanismo de aquí de Tenerife es como el de La Palma, ya vamos equivocados. Puede ser como el de La Palma o no. Es que puede ser explosivo, pero no se sabe.
Pero es una pregunta interesantísima, porque uno de los temas que ha estudiado otra estudiante nuestra que está ahora haciendo su doctorado en Cambridge, que está por empezar a publicar, es que en La Palma, por ejemplo, tenían la idea del volcán amable, ¿no? Del Teneguía. El Teneguía, que era casi un espectáculo de la naturaleza, que la gente se apuntaba con los billetes a ir en barco a verlo, se asomaban, llevaban el picnic. Y claro, todo era como muy folclórico, se hablaba como de eso de una forma muy romántica. Entonces, claro, cuando entró en erupción en el 2021 el Tajogaite, eso no tuvo nada que ver. Y parte, creo yo, también de ese impacto tan fuerte, ese shock que se llevó la gente, es porque tenían miembros de su familia que habían visto ya 2 volcanes, pero pensaban que era de otra forma. Y claro, ahora somos muchos viviendo en estas laderas y los impactos pueden ser mucho más dramáticos, ¿no? Yes, of course.
Sharon,
Okay,
if I
thank
could
you. So-
have just a moment to answer also Nieves, because I think that I also want to say something that I think that still having that bond with the people is very important. But I view it as, for example, like how do people learn? So some people learn more through repetition. Some people learn more through listening stuff. So I think going to the community and speaking to them is really important, but I think what's even more important is to have redundancy in the system. So as I said before, the pamphlets. So it's basically to have like a systems of methods to get in touch with them, so that even if maybe 99 of them fail, you still have that one system that really works. So for example, I use the example of the pamphlet. Even if someone hasn't attended to those talks, even if someone doesn't have social media, even if someone hasn't got any contacts in the village, they will still have that pamphlet that they picked up one day that they can still go and look to and know what to do.
Well, on the second question for Twitch about I don't know if it's like history matter. I don't know if you have studied about Alexandria, Nápoles in Italy. That's volcanic landscape. Cadiz or Port Royal near Jamestown in Jamaica. There are some historical places that have been sunken by earthquakes and well, Cadiz, no, the temple of Heracles that are sunken under the water. Maybe this kind of experience can help to make a plan of security. I don't know. I don't know if you know about that.
No, not really. Well, actually, I started 1 month and a half ago, and up to now I was doing only things at the macro scale, so everything is new to me. But maybe it would be great. The thing is, like in macro scale, there's many heterogeneities and macro scale processes that are so different that maybe it's worth to take into account that what happened in Cadiz or what happened in Naples, like the type of earthquakes or the type of landslide were completely different. So it would be very cool to have like a huge data set with different types of numerical simulations that you can easily run, and then you can see, okay, so it's more likely that this type of event will happen, or this one. Then it would be very important to be able to reproduce different geometries and different events that have very different origin, so you can have like a huge data set and then apply it to in emergency plans. Then that would be the way to go, I would say.
Lovely, thank you. Pablo, I think you have a question. No?
Actually, too. Thanks for all the talks during this session. For sure, I'm very fonded by your experience as postdoc. So I have a question for Jesus. You haven't been grilled yet. And another for Eduard. So Eduard first, I think it's relatively short. So that's your numerical method. You explain about the dense packing and the loose packing, but we know that geological material are very heterogeneous. So do you have the flexibility to switch or to create mixture behavior between the two members? Because I think it will be very interesting that you add this capability to your models. And the question for Jesus will be, maybe.
Yeah. Well, if you go to the microscale with the DEM, yes, for sure, because actually you're solving everything. You can put different materials, different shapes, different rocks, anything you can do. But the problem is you need computational wise, it's a disaster. You cannot do that. And when you upscale, not with the methods I was presenting, but with finite element methods. Actually, I guess you can probably distinguish different materials, associate different properties. In the ones I was presenting, not right now. I mean, you could actually introduce new equations and introduce new properties that need to be solved, but not in the current state, at least.
Thank you. Jesus, I'm fascinated with the possibility that we could extend volcano monitoring to the seafloor or near seafloor, but I don't know how flexible it is. What is your thoughts about the horizon, the time scale that a monitoring system could be implemented? Will send data in real time, and the real-time data will be ingested to improve earthquake locations, because I think your pilot is a pilot, but there's still so much to be done. So I'm keen to know your thoughts.
Yeah, thanks, because that's like the key question there. Well, there are like two big possibilities, and they are pretty costly at first. One of them is the cable hydrophones, that the installation it's costly, and then, well, maybe the maintenance not so much. But once you have a cable hydrophone, I don't know, to 80 meters depth, like we have here, then you feed this to the system, and you can prepare an automatic detector, and you can coordinate that with the IGN, for example. So yeah, that's like the more costly way. And then there's another where we could prepare buoys that are transferring the data that are already calculated. Like it's a hydrophone in a buoy with a GPS coordinated and with an automatic detector. And it's with a SIM card, it's transferring the data. This is used for other things. That's why I thought about it. But yeah, the two ways are very like costly at first, or to think of the logistics. But I think they are worth it to explore both of them. So yeah, let's see. Because yeah, we should I mean, the ideal way would be a cable hydrophone, because you can have all the data. Because with the transferring with a SIM card, it's only the detection, the processed data. The other way, you could use it for many other things that we really need. Like, for example, detecting the whales that are being killed by some of the ferries, for example, and at the same time, the earthquakes. So it would be like multi-purpose. So that would be the ideal way. But yeah, let's start with this super mini pilot, then another like boulder pilot, and building from there. But yeah, it's super interesting. Let's hope not.
Thank you. We have one more question before lunch from the floor, if we may, please.
Okay, thank you. Well, I would like first to congratulate you all, because the presentations have been really interesting. I have two questions, one for you in Spanish. José, tú has mencionado que hay dos flujos de lava y que en el frente de esos flujos de lava salen otros flujos más fluidos. El aporte de esos flujos es a través de un conducto subsuperficial, una especie de tubo volcánico.
En realidad eso se intuye, pero no se sabe porque está tapado por 25 metros de colada de esos lóbulos de las lavas AA. A veces, tú lo sabes muy bien, ocurre que las propias lavas más fluidas de tipo bajo ejue, cuando entran en contacto con cosas muy frías, pasan a lavas de tipo AA. Es probable que esté ocurriendo eso ahí, pero habrá que indagar un poco más. Y digamos que lo que tenemos es unas lavas que sí que van a generar ese espílulo, pero que la parte superior se enfría mucho más pasando a lavas AA, que de algún modo preservan el que esté caliente debajo. Es lo que se intuye, pero es que no podemos ver más.
Es que es muy interesante porque siempre se ha hablado de que los tubos volcánicos no se pueden formar bajo el agua, ¿no? Y,
aquí sí se ven.
Yo creo que es muy interesante. Vale. And the other question was for Juan Pablo. You have been talking about an hydrothermal system with CO2 emission. Have you checked the origin of this CO2?
Not really.
Okay.
Not really. I know that previous studies already detected this bubbling, but no, we just measure all the fluxes. But no, we don't know the origin.
It could be interesting. Thank you. Well, I don't want to. I have a lot of comments and so on, but during the
we have lunch. We can maybe speak over lunch, but thank you very much. I have to say, José Antonio, next time I go to La Palma, for anybody who doesn't have a boat like you or a submarine like you, but has an interest in pillow lavas, go for a hike in La Palma, Barranco de las Angustias. I will never be able to have that hike in the same way again, having heard you talk. So thank you. Speaking as an absolute non-scientist, it was really interesting. And thank you for that. Okay, thank you very much, everybody. That's about wraps it up for this session. We're going to have some lunch. We'll meet back here and start again at 3:30, I believe. Yeah, we look forward to the afternoon session, our new session on emergency management. Thank you.